Let's examine Charles' law as postulated by Jacques in 1787, in which he describes the effect of temperature on volume, the effect of temperature change on volume of gases. Charles' law states that the volume of a given mass of gas is directly proportional to its absolute temperature at constant pressure. Now, it has to be noted that the temperature has to be absolute temperature, which is temperature on Kelvin's scale. Now, recall that 273 Kelvin is equal to 0 degrees Celsius. So all calculations here must be converted to Kelvin temperature. So we have it that volume is directly proportional to temperature, which means that V is equal to kT. So K, meaning the constant of proportionality, is equal to V over T. Now we have it that V over T, the ratio of volume and temperature, is a constant, so that V1 over T1 is equal to V2 over T2. Kinetic theory explanation of Charles' law. An increase in temperature raises the average kinetic energy of the gas molecules, which means that as the temperature increases, the gas molecules are more energetic. Now, this would normally increase the rate of collision among the gas molecules and with the walls of the container. That is the pressure. But since the gas pressure is kept constant, it follows that in order to maintain a constant pressure while the temperature is increasing, the volume of the gas has to also increase proportionately, which means the space occupied by the gas molecules has to increase so as to accommodate the increased energy of the gas molecules. The converse is also the case. Now we have graphical representation of Charles' law. We have this, that the volume and the temperature are presented here. Now, you must include the unit. Here is the Kelvin, okay? Yes. And we have this other one where the unit used is degrees Celsius. So you see the dotted line, that is sub-0 degrees Celsius. Yes. It has to be noted that the temperature of minus 273 Kelvin is taken as absolute zero. At that temperature, there should be no kinetics. It's expected that there should be no movement in matter. Yes, although there has been no experiment that takes that checks the volume of gases to that extent, but that is a theoretical assumption. We can also use this graph to represent Charles' law. Now let's consider some examples. Number one, the volume of a fixed mass of gas is 3.0 dm cube at 27 degrees Celsius. What would its volume be should the temperature be raised to 127 degrees Celsius at constant pressure? This is Charles' law. So we see that we have the V1, that is the first volume, at 3.0 dm cube, and the first temperature is 27 degrees Celsius, and converting it to Kelvin, it gives us 300 Kelvin. The second temperature, being 127 Kelvin, is 400 Kelvin, and we are looking for the second volume. Using V1 over T1 is equal to V2 over T2, and making V2 the subject of formula, we have it that V2 is V1 T2 over T1, which is equal to 3 times 400 all over 300. And the answer is 4.0 dm cube. And the second example, a gas that fills a 3.25 dm cube vessel was allowed to expand to 9.75 dm cube at constant pressure. What would the ratio of its final temperature to its initial temperature be? All in Kelvin. And we have V1, of course, is 3.25 dm cube, and V2 is given to us also as 9.75 dm cube. And we are required to find the ratio of T2 to T1 using V1 over T1 is equal to V2 over T2. That is Charles' law. And rearranging the formula this way to give us V1 over T2 is equal to T1 over V2, so that V1 over V2 will be equal to T1 over T2. And rearranging the other way again, we have it that V2 over V1 is equal to T2 over T1. So we see that V1, the ratio of V2 to V1 is equal to the ratio of T2 to T1. And the ratio of the final volume to the initial volume gives us the ratio of final temperature to the initial temperature. Therefore, 9.75, that is final volume, to 3.25 will be equal to the ratio of T2, final temperature, to the initial temperature. So what we have to do is to divide the smaller of the two volumes. We use the smaller of the two volumes to divide the values. And dividing it, we have it that the ratio is 3 to 1. And that is the ratio of final temperature to initial temperature. Thank you very much, and watch out for our video on general gas law.